Summarizing IPv4 networks. This is a great skill. You're going to love this. Here are the opt-out questions for this video, and there's two ways to use these. Number one, read them right now, and if you know the answer, you can safely and comfortably join me in the next video. Secondly, if you're watching this video with me at the very end, after you've learned how to do summarization, you can come back to these opt-out questions to validate your newfound knowledge. Let's begin. I've got a question for you. Why in the world would we waste any time at all learning to summarize networks if we didn't need it? The reality is we absolutely need to do this, and it happens all the time. One example might be this. Let's say this is our company or branch office of your and my company, and we have some subnets. So it's the 1771, and then we have subnet 244, 246, 248, 250, 252, and 254. And you might say, hey, those are all incrementing by 2. And that would be because the mask of 23 has a block size of 2. And indeed it does. So let's say this branch of our company is connected to the internet, and we have a virtual private network over the internet connecting to our headquarters office. Now my question is, how many routes are we going to have on our corporate router here to reach the 244 and the 246 and the 248, etc. networks? Well, the first answer might be, well, we need 1, 2, 3, 4, 5, 6 routes. And we could easily do that. We could either dynamically learn 6 routes, or we could statically configure the 6 routes that go over this VPN. And with 6 routes or 6 networks, it's not a huge deal. However, think about this. What if we had 100 branch offices, and each of those branch offices had dozens and dozens of networks? Now we're taking a look at thousands and thousands of routes. If one of these networks has a problem or goes up or down, the routing table at our headquarters office is also going to reflect that. Using summarization buys us two things. Number one, we could have a summary route that says, hey, dear Mr. Headquarters Router, to get to all these guys, here's a single route to go ahead and use to reach all of those subnetworks. That's great. And secondly, because the headquarters router doesn't have to know the details of the 244 subnet or 246 subnet, if one of those networks goes down or has a problem, it's not changing the routing table on this headquarters router, which is already pretty busy already. So that is just one of many benefits of using summarization. We're also going to be using summarization techniques as we take a look at wildcard masks in access lists, as well as network statements in routing protocols such as EIGRP and OSPF. Now here's the million-dollar question. What is that magical summary route that can summarize all of these networks? So here's my question for you about summarization. Do all of these subnets under the 1771X, with X being the actual subnets, could we summarize those by using something like this, 17.0.0.0/8? Now, you and I both know what that 8 means. It means the first 8 bits are being used for the network, and the last 24 bits are not being used for the network address. So if we look at this network over here, do all of these subnets, do they all begin with 17? And the answer is, holy shnikers, they do. They all start with 17. So 17.0.0.0/8 would be a summary of all of these networks. Now, I'd like to share with you the problem of using this summary. What if we have another branch office that's using 17.42.x.0/23? This summary of 17 anything not only covers this whole area of our network, it also covers a network that's using 17.42. It also covers any networks that's using 17.49 or anything else that begins with 17. What this right here is an example of is a gross over summarization. In fact, do you want to see what the ultimate summarization is? It looks like this. You may recognize it. And that's what a default route looks like on a lot of routing devices. It effectively says the mask is a /0, which means everything matches. A default route is like the ultimate summarization because it covers the entire range of IPv4 addresses. That's why in a routing table, we have more specific routes that are used first. And if a router can't find a more specific route, the default route matches. Because it's effectively saying, I don't care what the address is, this is going to be a match with a /0 mask. So getting back to our point, we don't want to use a incorrect summarization that's summarizing additional networks above and beyond what we intended. I remember a movie back from the 80s called Top Gun, And in there's a quote that goes something like, "Son, your ego's writing checks your body can't cash." Well, in the case of a incorrect or a gross over-summarization, this summary is representing more, a whole bunch more, than just the subnetworks in a certain part of our network that we intended. So here's the process that you and I get to use to create an accurate summary for a set of subnetworks. It's these 4 steps right here. I'm going to walk you through them, and then I'm going to have you write out the steps, and then we'll do some exercises to practice those steps together. Our first step is to find the common ground between all of these subnets. So how many bits, starting from the left, in the IP address of those subnets, how many are common? And our address is 1771X, with X being that actual subnet. So here's what I can tell you, just by looking at this, because we have a /23 mask, the first 2 octets are going to be identical for all of those. So we know that the first 16 bits are all the same for each of these subnets. For example, it's going to be 1771 for subnet 244, 1771 for subnet 246, and all the way across the board. So we really don't need to slice and dice and dissect those 2 octets, because we know that all subnets are using those same 2 octets that are identical, and that's the first 16 bits. And now we come down to the actual subnet value here in this 3rd octet. So we're going to use our table up here for our 3rd octet, and let's go ahead and identify out of the 3rd octet what the common bits are. So our subnets are 244 and 246 and subnet 248 and subnet 250 and subnet 252 and subnet 254. Make sure I got all of them. So there's 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Okay, that's the 6 subnets that we want to create the summary for. And we know the first 2 octets are going to be 1771. Now what we need to do is find out from that 3rd octet how many of the bits out of all those addresses are exactly the same. Now here's my question. How in the world do we convert this decimal number of 244 and 246 and so forth into binary? Now, if you're saying at this moment, "Oh, nuts, I should have watched that video called Beautiful Binary and Binary to Decimal Conversion," because that's where those concepts were covered, I would strongly encourage you to pause this right now and go take a look at those videos. They will benefit you. If you've already been through those videos, you might be saying, "Oh, Keith, I got this." We're going to play the game called Does This Go Into? So we'll start with 128 and say, does that go into 244? And the answer is, for this guy, yes, it does. For 246, yes, 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 and yes. And then we're going to subtract 128 from each of those. So if we were going to do this longhand, which I'm going to do with you this first time, we go something like this. 244 minus 128, 246 minus 128. For this one, the remainder is 116. And all the other numbers were 2 higher than the previous, so the remainder is going to be 118, 120, 122, 124, and 126. And then we keep playing the game. Then we take the number of 64 and say, does that go into each one? And the answer is yes, it does. It goes into each of those results. So we have minus 64, minus 64, minus 64. Now after a while, you may be able to shortcut this a little bit, but for now, I would make sure that you know how to do it the long way. So the result of each of these would be 52 for this one, 54, 56, 58. And then we play the game again. So we got to say, now does 32 go into each of those? And you know what? It absolutely does. So we have a 1 in each of those positions, and we minus 32 from that. And with your permission, I'd like to bring my results up here because I'm out of room down here. So 52 minus 32 is 20. The next one's going to be 2 higher, 22, 24, 26, 28, and 30. And then we continue playing the game. Okay, does 16 go into each of those? And the answer is yes, it does. Minus 16, 16, 16, 16, 16, 16. It does go into each one of those, so we put a bit on in that position as well. And then we get our remainders. So the remainder here is 4. And then we have 6 and 8 and 10 and 12 and 14. And then we continue playing the game. So the next question is, does 8 go into 4? And the answer is no, it doesn't. So let's just do this column real quick. Does 8 go into 6 for the second network? The answer is no, it doesn't. Does 8 go into 8? And the answer is yes, it does. It goes in one time, so there's a minus 8 right there. And also 8 goes into 10, so minus 8 for a result of 2. And the next one and the next one, so we have minus 8, and we have 4 and 6 as results. Now as we move down to this next number of 4, it goes into this first one time, and that's minus 4, and he is out of the game, so it's 0, 0 for the rest of his bits in that octet. The 4 also goes into the 6, we'll put minus 4 here, the remainder is 2. And so we'll go ahead and put his 2 right there to finish him out. And then for this third subnet, he is done. He has no remainder there, so we're going to 0 that guy out. The next subnet, we have a 2 left, so that 2 goes right there. Everything else is zeroed out. The next subnet has a 4 left over, so we know that the 4 goes in one time, everything else is zeroed out. Again, it's like an accounting game. We're getting down to 0. And then for 6 here, we're going to have a 1, which is minus 4, a 2 left, and then we have a 2, which is minus 2, and we're at 0 there as well. So there's the binary equivalent of each of those. If you'd like to brush up on your practice for conversion of decimal to binary, the 2 videos I'd recommend you watch again are Beautiful Binary in this course and the binary to decimal conversion video. Between those 2 videos, it has all the details regarding what we're reviewing as far as the conversion process that we're doing right here. So that was step number 1, finding the common bits. And I'll walk you through another scenario here in just a moment, and I'll show you a little shortcut to this process. But I want to make sure that you had the details behind the scenes of what's really happening. So we found the common bits. And the common bits, if we look from left to right, the common bits between all of these 6 networks is right there. Because if we go any further to the right, they start to not be the same as each other. And all we're going to do is we are going to go ahead and use that as our new mask boundary. So our mask is going to go all the way up to these first 4 bits. And then step 3 says we're going to go ahead and 0 out everything to the right. Just pretend it doesn't even exist for the purpose of our summary address that we're creating. And then indicate that new summary and the mask. So the new summary would be 17.71. Those first 2 octets have not changed. We take the value of these 4 common bits out of each of the subnets, and it would be 128 plus 64 plus 32 plus 16. The sum of those 4 high order bits are 240, so it would be 240.0. We 0 out everything to the right, and that new mask would be how many bits? How many bits from left to right for the entire IP address are we now representing as a network address? And the answer is we have 8 here and 8 here, which is 16. Plus, we have 4 more, which would be 17, 18, 19, 20. So our new mask would be a /20. So 17.71.240.0/20 is a summary address that closely represents these 6 subnets. So what I'd like you to do is I'd like you to write out these steps, steps 1, 2, 3, and 4. Take a moment, pause, write out those steps, and then we're going to do another exercise together, and I'm going to change the subnet numbers so we aren't working with the exact same numbers as we were previously. Pause me now. When you've got them written down, go ahead and click on Resume. So let's mix it up a little bit. We'll still use a /23-bit mask, but for our subnets, let's go ahead and use subnet. Let's use 52 for here, and 54, and 56, 58. Down here we'll have 60, and over here we'll have 62. So our objective is to create one summary for all these 6 networks. So the first step is to find the common bits. Up here for these subnets, we have 52, and 54, and 56, and 58, and 60, and 62. If we play the does it go into game, we know that 128 doesn't go into any of those numbers. And if we want to just do one network at a time, for example, this octet of 52, we know there's no 64s. There's a 32 in there, which has 20 left over. So out of that 20 left over, we have a 16. Then there's 4 left over. We have a 4, and all the rest are zeros. By practicing the decimal to binary conversion, you'll get faster and faster at doing it without having to write it out longhand. And for these others, which I know are just 2 more, I can just go ahead and use the same numbers up to that point and add the 2. So that is 2 more than the previous one. And then for 56, I need to add 2 more here. So I'm going to 0, 1, 1. And it gets a little bit tricky when you're adding in binary, because if we add 1 to this position, those 2 roll over. So it would actually look like this, 1, 0, 0, 0. And this next one is 2 more. And this next one is 2 more than the previous one. So again, we're adding a 1 here because it's binary, there's only two positions, we are going to carry the 1. It's going to look like that. And for 62, it's going to be 2 more. So it's going to be 0, 1, 1, 1, 1, 1, 0. And if you want to do it longhand and just verify your work, that's perfectly fine. There's no harm in that at all. But the reality is we do have to find out what the binary is so we can draw the line regarding the common bits. And just to double check our work, if we wanted to verify that 62 really is this number, we could say 32 plus 16 plus 8 plus 4 plus 2 is, and add those up. So 6 plus 2 is 8, 8 and 8 is 16, plus 4 more is 20, plus 2 is 22, so we carry the 2 up here, bring the 2 down there, and then add up the tens position. 3 plus 2 is 5, plus 1 more is 6, 62. Just to validate that we didn't get our math somewhere wrong in the process. So there's the binary representation of those 6 subnets, and all we do is we find out where the bits are in common. So the 128-bit is in common, the 64-bit's in common, the 32, the 16, and you know what? That's where the dividing line is, right there, because after that point, they start not being common anymore. So that's our very first step, find the common ground, the common bits going from left to right. Second, use the mask to cover the common bits. So this new mask is going to be shorter. We are creating a summary, which means a shorter mask to summarize multiple networks or subnetworks. So the new mask is going to be the first 8 bits plus the next 8 bits, and then we are using the first 4 bits of that third octet. Now check this out. As we write this out, 17.71 what do we put for these 4 bits? You put whatever the value is of those 4 common bits, which are 0 plus 0, there's no 128s, no 64s, 32 plus 16, which is 48 right there. So that's 48, and then we zero out everything else. And the new mask is going to be 16 plus 4 more bits for the mask. So it'd be 16, 17, 18, 19, 20, and that new mask would be 20, representing the length of the common bits. So this 48 is the value of those common bits in that third octet. And that /20 is representing how many of those bits are in common. So the Reader's Digest version of this says the first 20 bits of all of these subnets are identical to each other. And that's what makes this summary address appropriate to represent these 6 subnets, because they all have the same first 20 bits. So let's do another one. So you should have these 4 steps written out so that you can go ahead and follow the process. And here's what I'd like to do. Let's go and use 95.0.0.0/11. So our block size is 32. And what I'd like to do is let's go ahead and let's create a summary for the 0 subnet, for the 32 subnet, for the 64, and the 96 subnet. So that's the first 4 subnets that we could carve out using 95.0.0.0/11. And of course, this 95 would be brought down for each of those. And here is your expert exercise right now. Using these 4 steps, I'd like you to identify a summary address for these first 4 subnets of the 95.0.0.0/11 address space. So go ahead and pause me right now, do that exercise, and when you're done, click on play, and you and I will compare notes of exactly what we came up with. Here's how I would approach this. The first step is to go ahead and say, well, what are the common bits between these 4 subnets? And we have to calculate what the binary values are. So for 0 subnet, 32, 64, and 96, we can basically say, well, 0 is all zeros. That was pretty straightforward and easy. 32 has 132 and the rest are zeros. 64 has a 64 and all the rest are zeros. And 96 has a 64 and a 32. And the more you do this math and practice with those conversions, the faster you will become. So out of all these bits going from left to right, which bits are in common? Well, it looks like just this column right here, the 128th position, and then after that, they've all got different values. So our new mask is going to be drawn right here. So just as a reminder, the original mask, 95.0.0.0/11, the original mask is here, this blue line, and our new summary is going to be this green line. So this second step is we are now going to use a mask to identify what those common bits are. So the first octet of 95 is common to all 4 subnets, and this very first bit of the second octet is also common. So our new mask is going to be a /9. This is the new mask for the summary. Whenever we're doing summarization, the mask is going to be shorter to summarize a larger quantity of networks that are being summarized beneath that. The third step is to go ahead and zero out the rest. So in this case, the first octet is going to be 95. We then represent whatever the value is of this 128 position, which happens to be 0, and then everything to the right of that gets zeroed out as well. So our summary address is going to be 95.0 because we had nothing on in those common bits between the 4 subnets. So we don't put any value there, and then we zero out everything to the right and put the new mask on, a /9. And that's step number 4. Indicate the new summary and the mask. So 95.000/9 is a summary of those 4 subnets. And I also want to point out that if we had said 10 accidentally and said the line's right here after the 64-bit, these bits in this 64 position aren't the same. It wouldn't correctly summarize those 4 networks because these bits in this 64 position are not the same between all 4 networks. So let's do another one with the 33.33 network .0.0/ and let's go ahead and use a 22. And let's summarize a few of the subnets in that range. Let's go ahead and summarize subnet 44. Again, this third octet is where we're going to be looking. And 48, and 52, and 56. So what I'd like you to do right now, using this 4-step process, go ahead and pause me. Work through the process as we've done previously. Figure out what the correct summary address is for just those 4 subnets. And then resume me and we'll compare notes. Alright, step number 1. Find the common ground, the common bits in that third octet. Because we already know that the first 2 octets are all exactly the same for all those subnets. So we're really just slicing and dicing this third octet. So we have 44, and 48, and 52, and 56. So for 44, we know, first of all, we know that 128 doesn't go into that, and 64 doesn't go into 44, but 32 does. So 44 minus 32 has a remainder of 12. So 16 does not go into 12, but 8 does, and 12 minus 8 is 4. So 4 goes in, and then we have nothing left over. So that's 44. Do the same thing for 48. 128 doesn't go in, 64 doesn't go in, 32 does go in. That has a remainder of 16, and that makes 16 go in one time, and we are out. So there's no more value left, so we're going to put zeros. Then we take 52. Now I know 52 is 4 more than 48, so we're going to add a bit here, and all the other bits are going to be the same because it's 4 higher, and 56 is 4 higher as well. So it's going to be 0, 0, 1, 1. We have to carry the 1. That's going to be a 0, 0, 0. And you may just want to spot check 1 or 2 just to make sure that you've got the conversion correct. So in the case of 56, if we just want to spot check, we have 32 plus 16, which is 48, plus 8 more, equals 56, and all the rest would be zeros because that's perfect. So the next step is to use the mask to cover the common bits. So if we go from left to right, how many of these bits are common? And I'm seeing all the way up to this point right here, because beyond this point, they're not common. So we already have 16 bits in common for the first 2 octets, and the first 3 bits of that third octet are also in common. So the mask for our summary is going to be 19, which is 16 representing the first 2 octets, which are going to be identical, and the first 3 bits of the third octet, which are also identical. So our new mask is /19. That's step number 2. We're going to not worry about the rest of these bits because the mask only goes up to this point. That's step number 3. And then we're going to indicate the new summary along with the mask. So the new summary is going to be 33.33, these first 2 octets which are identical, and then whatever the value is of these 3 common bits that are the same for all these subnets. So because there's 001, we have no 128s, no 64s, we have a 32, and that is the value of that third octet. And then after that, we zero out everything to the end of the IP address. So the summary address that identifies these 4 subnets is 33.33.32.0/19. Now I do have an observation that I want to share with you, and that is this summary isn't only for these 4 networks. We also are very likely going to capture any other subnets that have these high 3-order bits in common. For example, if we had 33.33.33 40.0/22 as one of our subnets. In fact, it's the subnet before this guy right here. Would that be included as part of our summary? And if we take a look at 40, I'll put it in green as well. If we have 40 right here, it's going to be 0, 0, 1. That's 32, plus 8 more, which would be 0, 1. And then these would be zeroed out. And check it out. Because its 3 high-order bits right there are also 0, 0, 1, this summary address also would include the 40 subnetwork. So at the end of the day, this summary address that we created is a good summary for these 4 networks. It's not watertight, but it's very, very close. And as network designers build IP addressing schemes, what they're going to do is strategically place groups of IP addresses and subnets in various parts of the network so that when it does come to summarization, they can get very nice and clean summarization boundaries that won't over-summarize any additional networks. But to do that, it never happens by accident. It's only through planning. Our action items for this video are simple. Number 1, make sure you've done the expert exercises together with me in this video so you can correctly create a summary address for a group of subnetworks. And secondly, I'd like you to take just a moment and review the opt-out questions at the beginning of this video. Now, the reason for that is because once we've gone through this together, it'll help reinforce the concepts we've learned, and secondly, it will help validate that you currently can create a summary address given a set of IP subnetworks. I hope this has been informative for you, and I'd like to thank you for viewing.